Welcome back. This is COT 3100. Today's topic that we want to discuss is Chapter 4, Number Theory and Cryptography. This chapter mainly talks about the number theory and some application of it. And it is an essential part of computer science, and its application is all over the computer science and what we do in today's world. Let's number theory is the part of mathematics devoted to study of integers and their properties. All right, we look at the numbers, how we value the numbers, what is the meaning of the numbers, and what are the properties and how the numbers are related to each other. And we study this, and we look at some, mainly the applications that we use in computer science and information technology today. So we're going to look at the divisibility and modular arithmetic. Then we're going to look at integer representation and algorithms, meaning the base of the numbers. And then also we're going to look at the primes and the greatest common divisors. And also we will look at some applications, and finally we discuss briefly about cryptography, what it is. And so this is going to take about 4 or 5 lectures, which we should do it within next 10 days. The first thing that we want to discuss is the divisibility and modular arithmetic. We want to know if two numbers are divisible, all right? And if they're not divisible, what's the remainder? Remainder, in a lot of situations in the computer science, the remainder is very important for us because we need to know what is, how much is the leftover and what we do with that one. And the application of it in the computer science is basically, it's extremely high, and we always use this remainder concept. And so we're going to look at the division algorithm, and modular arithmetic. Let's look at the division first. We say, here's the official definition: if A and B are integers and A is a non-zero value, all right? A is a non-zero value because we're going to look at the B divided by A, all right? So denomination can never be 0. If it is 0, it is an unknown factor in mathematics, and you will see why and here actually you will notice why that's the case, because we say A, the denominator, divides B, the numerator, if there exists an integer C such that B is equal A times C. Basically what we are saying, for example, 10 is divided by 5, all right? Here 10 is B, A is 5. It's equal to 2, all right? So we're saying 10 is equal 2 times 5, right? So basically we want to know how many values of that, the number of the values of the denominator is in numerator, right? So if you have a 0, how are you going to calculate that one? You don't know how many 0 fits in 10. We don't have that in the mathematics. That's why we say A, or the denominator in this case, has to be a non-zero value. So we say when A divides B, we say that A is a factor or divisor of B, all right? So A is a divisor of B, or we say A is a factor of B. Factor comes from this statement, B is equal AC. So A, we say, is a factor of B, meaning it's multiplied by another non-integer, will give me B, all right? Or we say it's a divisor, meaning that A, B can be divided by A, and the result is C, all right? So b, and that b is a multiple of a. Again, it comes from here. The notation a, straight line b, denotes that a divides b. All right? Now, if a divides b, then b over a is an integer, right? There's no remainder if it divides. If a does not divide b, we write a, we put this straight line, then we put a cross line. That means that a does not divide b, and there is a remainder if we do that operation. For example, 3 over and 7, all right? 7 over 3 is 2 point something. It's not an integer, so it does not divide. 12 over 3, it gives me 4, so this is divisible. Properties of divisibility now. Let a, b, and c be integers, all right, where a is not 0. If a divides b and a also divides c, then a divides b plus c. All right? This is a theorem, and there is a proof here. If a divides b, then a divides b times c. Well, of course, for example, again, let's go back to the example of the 10 over 5. 10 over 5, what I'm saying here, if 5 divides 10, all right, which we call that denominator divisor in this case, if 5 is a divisor, then clearly 5 also divides 10 times 6, 10 times whatever integer is. So that's why we say here, and then a also divides b for all integers c. If a divides b and b divides c, clearly a also divides c. It's divisible. Proof, it's very simple and straightforward here. I don't want to discuss it because we're not that concerned with that part. Division algorithm. What is division algorithm? When an integer is divided by a positive integer, there is a quotient, right? 9 divided by 5. How many 5 is in 9? Just 1, right? That 1 is called quotient. And a remainder. 5 minus 9, that's 4. That's a remainder. So, whenever we divide, let's say 16 divided by 5. 16 divided by 5, the quotient is 3 and remainder is 1. All right? And remainder is 1. So we say, here is the algorithm. If a is an integer and d is a positive integer, then there are unique integers q and r. Q stands for quotient, r stands for remainder, with r less than d, well, has to be less than d, right? If it was more than d, if you're dividing 16 by 5, the remainder cannot be more than 5, right? And so, with the r has to be a value between d and greater than 0, such that a is equal dq plus r. In case of 16 divided by 5, then 16 divided by 5 is 16 is equal to 16 divided by 5, quotient is 3, right? Quotient is 3. So 3 times 5 is 15, remainder is 1, plus 1, 16. So a was 16. So has to be a number that satisfies this equation. Now, how do we write this one? Q, quotient, is always equal to a divided by d. 16 divided by 5, quotient is 3. Remainder is a mod d, meaning if you divide a by d, whatever is remainder is equal, or it's r. So d is called the divisor, is the denominator. A is called the dividend, which is the numerator. Q is called the quotient, is the result of that division, only integer part. And R is called the remainder part. All right? Here are some examples. What are the quotient and remainder when 101 is divided by 11? Well, if 101 is divided by 11, quotient is 9. What's the remainder? 2. Right? 9 times 11, that's 99. Right? The remainder is 2 because the 99 plus 2 is equal to 101. Remember that remainder cannot be greater than or equal to the divisor. So, and then what's the R? A mod D, 101 mod 11, meaning you divide 101 by 11, whatever it is the remainder is equal to. Right? Quotient is 9. 101 divided by 11. There are 9 11s in 101. And what is left? 2. Here's one tricky one. What are the quotient and remainder when minus 11 is divided by 3? Keep in mind that we did not say it says when an integer is divided by a positive integer, right? By positive integer, but we didn't say, here we didn't say when a positive integer, right? So dividend could be a negative number. Minus 11 is divided by 3. What would that be? Well, here's the solution. It would be minus 4. The reason is we say 11 divided by 11 divided by 3, minus 11 divided by 3, we say it is minus 4, and then the remainder is plus 1, right? Then the remainder is plus 1, and that solves my issue, because minus 3, 11 divided by 3, remainder is 1, all right? And the other one, we say it is minus 4. Because of the minus plus things, because minus 4 times 3, I have to put them in this equation. If it satisfies this equation, then it is correct, right? Minus 4 times 3 is what? Minus 12 plus 1 is minus 11. A was minus 11, right? A was minus 11. And we will never get the negative R because you cannot have negative remainder. Why? Because remainder has to be smaller than dividend, right? Smaller than divisor, and greater than or equal to 0. So R cannot be a negative number. For that reason, 11 divided by minus 11 divided by 3, we say it is minus 4. Then minus 4 times 3, that's 12, minus 12, plus remainder has to be 1 to make him equal to minus 11. Congruence relations, what is that? If A and B are integers, and M is a positive integer, then A is congruent to B modulo M if M divides A minus B. All right? If A divides minus B, A minus B. So let's take a look at, we look at some examples and we make it clear. The notation A, 3 straight lines, B mod M says that A is a congruent to B modulo M. That's what it means. We say that A is a congruent or A congruent to B mod M, and that M is its modulus. two integers are congruent mod m if and only if they have the same remainder when divided by m. So basically I'm saying I have two numbers, two integers, a and b. They both, if are divided by m, produce the same remainder. All right? If they both are divided, for example, 16 and 11. Right? If they are divided, 16 and 11, if they both are divided by 5, they both generate the remainder, same remainder, which would be 1. So if two numbers are divided by the same integer and produce the same remainder, then we say those two numbers are congruent, modulo that integer. And so that's why we say A is congruent to B mod M. All right? And if A is not congruent to B modulo M, we just cross that one. Now, determine whether it's 70. How do we know two numbers if are divided by? How do we know if two numbers divided by a fixed integer or certain integer, they create same remainder? If those two numbers subtracted from each other are divisible by m, by that specific integer, as we said it here. We said if a and b are integers and m is a positive integer, then a is congruent to b modulo m if m divides a minus b. Meaning you calculate a minus b, those two integers, and divide them by m, and you get an integer, no remainder. Here's an example. Determine whether 17 is congruent to 5 modulo 6. Well, 17 minus 5 is what? 12, right? A minus b. 17 minus 5 is 12. Is 12 divisible by 6? Yes. So this one is congruent. 24 and 14 are congruent to modulo 6. Well, 24 minus 14, that's 10. Is 10 divisible by 6? No, right? Because it produces a remainder of 4. Therefore, these two, 24 and 14, are not congruent modulo 6. We write them like this. But 17 and 15 are congruent numbers modulo m, and we write them like this. And here's the solution. It's not. Okay. Let m be a positive integer. All right. Any number, positive integer, anything 1, 2, 3, anything positive integer. The integers a and b are congruent modulo m if and only if there is an integer k such that a is equal b plus k times m. It's a theorem, and we can easily prove it, but you need to just know the theorem at this point. All right? And so we say there is in order to make sure that two numbers are congruent, one was that we say we did subtract those two numbers from each other and divide them by that integer m. If it is divisible, we say they are congruent. And also, we can say two numbers are congruent modulo m if there exists an integer k such that a is equal b plus km. All right? And, and here's the solution that you can read it. The use of mode in a, b modulo m, and a mod m are different, right? Because here we are talking about congruent numbers. Here we are talking about their remainder. A congruent is congruent, a and b are congruent in mod m is a relation on the set of integers, because those two numbers, they both are when they are divided by m, they generate the same remainder. In an A mode n, the notation mode denotes a function because we're talking about the remainder of just A divided by n. The relationship between these notation is made clear in this theorem. Let A and B be integers and let n be a positive integer. Then A is congruent, A and B are congruent when the mode n, if and only if A mode m is equal to B mode m, right? What's that mean? Meaning that if A divided by m generates a remainder, and it is equal to if B divided by m, that generates a same remainder. All right, that's the basic definition. Also, this theorem it's good to know, and let m be a positive integer. If A is congruent to B mode m and C is congruent to D mode m, then we can say A plus C, the other one, is congruent to B plus D mode m. And also A times A is to B mode m and C and D mode m, right? Then I will say, all right, then A plus C is congruent to B plus D mode m. And also we can say A times C is congruent to B2 times D mode m. Meaning still they generate the same remainder. Let's take a look at an example here. For example, we say F7 is congruent to 2 mode m. That means 7 and 2, all right, and 11 is congruent 1 to mode m. It follows from theorem 5 that 7 plus 11 is equal to 2 plus 1 modular m. They both create, remainder is 3. All right, the remainder is 3. And if multiply them again, this should be 2 times 1, not 2 plus, all right? And this is 7 times 11 and 2 times 1, and so it becomes 3. So 77 modulo 5 divided by, if 77, all right, 77, if you take a, basically I'm saying the 77 divided by 5 creates the same remainder as 3 divided by 5. All right, and the same way here, 18 and 3. And as you see, they all 18 divided by 5, what is the remainder? It's 3 because we just calculated that one. And 77 divided by 5 creates also. Because 2 times 1, this is 2, it's not 3, all right? 2 times 1, this is 2. 77 divided by 5, remainder is 2. And these are some algebraic multiple manipulation, which is very same stuff as we just discussed over there, and it gives you more definitions of the same things that I'm not interested in doing it. Here is another issue that you need to know. Let Z sub m be the set of non-negative integers less than m, all right? Less than, let's say, 10. Then would be 0, 1, all the way till 9, right? So it's 0, 1, 2, 3, all the way up to m minus 1. The operation plus sub m is defined as a plus sub mb. It is same as saying a plus b mod m, meaning a plus b divided by m. It gets this remainder. This is addition modulo m. And the operation dot m, which is plus, this multiplication is defined as a dot m, b, this should be a times b, not plus, a times b mod m. This is multiplication modular. Using this operation is said to be doing arithmetic modular m. For example, 7 plus 1 sub 9, and what is that? This means 7 plus 1 9 means 7 plus 9, all right, is what? 7 plus 9 is 16, modular 11, there's only 1, and remainder would be what? 16. Modular, there is only 1 11 in 16, right? So 11 minus 16 would be 5. And it's the same thing here. So 7.9, 7 times 9 mod 11, 7 times 9 is 63 mod 11. And so if you divide 63 by 11, the remainder is 8. That is what we are talking about. And it keeps going arithmetic. The operations plus m satisfy many of the same properties as ordinary addition and multiplication. It's the same stuff as the other ones that we're trying to see it. And we're not that interested in that part. The next topic that I want to discuss is integer representation and algorithms. Integer representation, we always use base 10. All right, we want to see the anatomy of a number in base 10, in base 2, base 8, base 16, base 7, base 20, base 60, right? Base 60 years and years and years ago was very popular. That's where the 1 minute 60 seconds and 60 minutes 1 hour comes from, right? And base 20 was very popular in the very old Europe. That's where their grading system at universities are still based 0 to 20, not 0 to 100. And there are many of these concepts that we want to look at how we represent integers or the anatomy of integers. And that will be my next topic that I would like to discuss. And that would be our next lecture. And I will see you then.